Macroscopic physical properties, like a food's texture, stability, and digestibility, are strictly the result of its molecular-level structural organization. Bulk rheology tests an entire sample at once. It measures the average response, completely masking the nanoscale structural variations that actually govern the material's behavior under stress. High-vacuum electron microscopy provides a closer look, but it requires dehydrating the sample. This destroys the water-rich state of biological materials, rendering the structural data largely irrelevant to real-world conditions. Analyzing complex biomaterials requires capturing localized physical interactions without altering the sample. We need a way to measure them in their fully hydrated, native environments. Atomic Force Microscopy, or AFM, maps materials using a physical probe rather than light or electrons. Over the last decade, it has evolved from a tool for static surface imaging into an analytical platform for mechanical prediction. This diagram outlines AFM's operational scope. By applying specific measurement modes, researchers map properties ranging from viscoelasticity to surface friction. This directly links structural data to real-world applications, including taste and mouthfeel. The probe quantifies interactions down to the piconewton level. This translates otherwise invisible molecular forces into actionable mechanical data. Soft matter engineering is shifting. We are now using these molecular interactions to predict sensory and stability metrics from first principles. Extracting mechanical data from a delicate, hydrated biological sample requires a highly controlled physical interaction. This AFM force indentation curve tracks a tip approaching a surface. Suddenly, capillary forces pull the tip sharply downward. As it pushes into the material, the slope represents physical deformation. Upon retracting, the probe resists. This deep trough measures the exact adhesion force. Applying contact mechanics models to this raw data allows researchers to extract a precise Young's modulus for that exact nanometer of physical space. This method captures an enormous range of biological stiffness. It maps materials like brain tissue at 10 kilopascals, all the way up to rigid structures like walnut shells exceeding 1 million kilopascals. This single force distance curve converts a microscopic topography probe into a precise, predictive mechanical sensor. A single point of data is only the baseline. Arraying thousands of these force measurements across a biological matrix generates a highly detailed spatial map. Consider plant tissue degrading over time. Bulk compression confirms the overall structure is softening, but it cannot pinpoint where the precise architectural failure is occurring. Point data compiles into a tissue heat map. Red indicates high stiffness networks, while blue reveals low stiffness regions. Overlaying these onto cellulose fibrils identifies degradation specifically within pectin bridges. These distribution curves quantify this structural failure, tracking the localized modulus drop over 80 days. Macroscopic softening is the measurable result of localized mechanical breakdown within specific interfacial networks. This nanomechanical mapping extends beyond solid structures into fluid dynamics, specifically the stability of emulsions and foams. In a liquid matrix, overall stability is dictated by the microscopic boundary layer separating the oil and water phases. Proteins organize at this boundary, creating a physical barrier. We can probe this exact interface, pushing into a single nanometer-thick layer of molecules. The packing density of the protein layer actively resists the tip's downward pressure before yielding to a breakthrough force. Measuring the viscoelasticity of this specific boundary layer provides direct data on the bulk emulsion's ability to resist coalescence and separation over months of shelf life. Two formulations with identical bulk rheology profiles can behave differently over time because stability depends on specific nanoscale interfacial metrics. The same physical parameters that govern stability also define the end user's sensory experience. Mouthfeel is strictly the result of quantifiable physical interactions between complex soft matter and human oral tissue during the process of mastication. We can correlate subjective sensory terms directly with objective mechanical parameters captured by the AFM probe. Lower, highly elastic indentation moduli, measured in the single kilopascal range, physically translate into the human sensation of creaminess. Conversely, high pull-off forces, which are captured strictly during the tip's retraction phase, govern the perception of stickiness and mouth coating behavior. subjective taste panel results can now be reverse engineered into strict, objective mechanical targets. Mapping physical mechanics perfectly leaves one major analytical gap. Atomic force microscopy cannot identify chemical composition. Two structurally identical stiffness spikes mapped by the probe could represent entirely different molecular compounds, each requiring a different engineering solution. This is resolved by integrating Raman spectroscopy, which provides simultaneous molecular fingerprinting alongside the mechanical mapping. This setup overlays the physical landscape with the chemical landscape. The topographical map on the left matches perfectly to the confocal Raman spectroscopy map on the right. These specific spectral peaks confirm the exact chemical identity of the physical structures identified by the physical probe. Researchers can definitively link a localized change in physical texture to a specific molecular event, whether that is a protein conformation shift or a lipid phase change. Generating these correlated mechanical and chemical data arrays at high speeds produces an overwhelming volume of complex information. This schematic illustrates the implementation of artificial intelligence to process these massive datasets. Surface morphology and adhesion data are fed directly through a multi-scale convolutional neural network. Machine learning models ingest this multi-parametric input to instantly classify material behaviors and predict shelf life degradation long before it visibly occurs. By integrating piconewton mechanics, advanced molecular spectroscopy, and artificial intelligence, soft matter engineering can move toward atom-up synthesis, replacing much of the traditional bulk mixing guesswork with